So we'll still look at the warm-up quiz and go over it. Um, Let me share my screen. So we can see for the people who did actually do it, a lot of people did well, which is good. Again, these are only worth 1 point. So, every sub question is worth like 0.2 points. So the point of this is not about like getting points that are going to help your grade in any major way. It's more to just check in and see if you're keeping up, see if you're getting the concepts. Um, if here we see a couple that are down like 40 or 60%, if you start consistently getting your warm-up quizzes down here, that's a sign that you probably need to put a little more energy into kind of studying along the way and keeping up with the material as we go, because otherwise, like I mentioned, everything just keeps building on each other. And the stuff we talk about as we continue on in the signaling in the cell, none of that will make sense if the key chemistry concepts aren't making sense. So you really do need to keep up and not kind of wait till, if you wait till the week before the exam to like really figure it all out, you'll probably fail, right? That just doesn't work for this kind of class. You really need to kind of keep up as we're going. Okie dokie. Let's look at item analysis. No, not item analysis. I want to cancel. Oh, here we can just go down. Which is the following as an example of negative feedback. This goes back to the very first day of our class. And most people got this. Negative feedback. There's a response to a change in a variable that opposes that change. So if your body temperature is falling, the response is you shiver to warm you back up. If your body temperature is getting too hot, what would happen?
You would sweat.
You'd sweat.
Sweating to kind of cool back down, right? This platelets sensing a tear attract even more platelets. That would be an example of, this positive feedback, which we said is rare, but does happen. It's where we intensify the change. Stomach starts secreting acid to prepare for a meal you are about to eat. We talked about feed forward. We'll see a bit, we will see this when we get to the digestive system. Your pituitary gland releases this, adrenocorticotropic hormone, which causes the adrenal gland to secrete cortisol. This is more of just kind of control. There's no feedback happening here. Ultimately, there is going to be feedback where the cortisol comes back to the pituitary gland, but that is not apparent in this little, thing here. But these feedback loops are going to be at the core of so much of the control of processes in your body. So really having an intuitive sense for how that works is important for the semester. Non-polar molecules. This was kind of gratifying to see. Everybody said, do not dissolve in water, right? They don't dissolve in water because water is a polar solvent. Water molecules have that charge imbalance, and they like to, do this little dance with other molecules that are also polar. So if you have things that are non-polar, they tend to just get pushed off to the side. We call them hydrophobic. Separate individual. Oh, this was also people got. Separate individual water molecules are attracted to one another by hydrogen bonds. Again, these are these electrostatic attractions, things that one thing's a bit more positive, one's a bit more negative, and opposites attract. Which of the following would conduct electricity well? I don't see what all of the...
Professor, I was going to ask you about that one because I got it marked as wrong, but I put the NaCl solution and the Ca, the calcium chloride solution.
Those would be the ones that would be correct.
Yeah, and it marked it as incorrect because the other ones I think were distilled H2O, olive oil. Yeah.
Yeah,
I
that's
had the
what I
same
did too.
experience.
So there could have, I can check out, there could have been a problem with the way the question was created.
Yeah, same thing happened to me.
Yeah, so I'll take a look at that. But yeah, it should be the electrolytes. Sodium chloride would conduct electricity, calcium chloride would, oil obviously not. Sugar, would sugar conduct electricity?
No.
Right. It would dissolve, but it won't conduct electricity because there's no ions floating around. When ionically bonded, compounds such as sodium chloride are dissolved in water. So most people got this. They dissociate into individual ions. It's going to be important. We'll see this in much more detail today as we start getting into osmolarity and stuff. They dissolve. They do not stay intact as an intact molecule. Right? Each individual sodium and chlorine becomes its own independent little ion floating around in the solution. Definitely don't form covalent bonds with the water molecules. So, okie dokie. So, again, there was lots more we covered as well, but just kind of reiterating, the chemistry is at the core of everything. So make sure that these things are starting to feel kind of intuitive and comfortable, because I'll just start talking about, oh, this molecule's making a hydrogen bond with this part and a covalent bond or an ionic bond and blah, blah, blah. And just assume that you are comfortable and you know what I'm talking about. All right. So, I guess we're going to continue with the chemistry. Let's do this. Oh, I am recording. Okay, good. I think I have it set up to auto record now, so I can't accidentally forget. We're going to do the whiteboard. So this is basically, and actually I should ask before we get into new stuff. Are there any questions about the old stuff before we dig into the new stuff? Any points of clarification?
I didn't have questions about that, but I did have questions about when the tutoring center was open to review with somebody.
So I haven't heard from them. Normally they email me, but I can, during the break, I'll email Oksana and see what they have to say.
Because I kind of searched around Canvas trying to find something and I didn't find any information.
All right, here, I'm writing a note to myself. So when we take a break between lecture and lab, I will reach out to the tutoring center and see if they have any news. That'll be helpful.
Okay, I really appreciate it.
Okay. Yeah, and again, like I said, normally they send me an email. Typically, they have to wait to see what the need is. Like people reach out and fill out forms so they can decide how many tutoring hours should they allocate towards one topic or another. But they haven't even, usually they give us these forms where people can, where they come visit our classes even, so you know where to go and tell them that you want tutoring. All right, so chemistry review continues. Okie dokie. All right, so we've been talking about the basics of atoms and then how the atoms get connected together in molecules. So let's review just briefly the processes where molecules get created or where they swap parts and pieces and make new molecules. So let's talk a bit about chemical equations, or chemical reactions. And I should mention, for whatever reason, I learned using the abbreviation RXNs. So I'll write RXNs instead of writing reactions. It's just quicker. Um, so let's think about a few different things. Let's think about what kind of types are there. What are the different kind of major types of chemical reactions we tend to see?
Combustion.
So combustion, that would be kind of an example. That's a specific example of a more general thing where things are breaking apart. So that would be like, we'd call like decomposition or like catabolism, where you have something that turns into different parts. So that's one type where things break apart.
Synthesis.
Yeah, obviously there's going to be synthesis, or we call anabolism, where you have things that become a single thing.
Decomposition.
What's that?
Decomposition is. Oh, sorry. Or single displacement.
So there's like exchange or displacement. Where you have like, A, B plus C. Actually, let's make the C blue to make it easier. Becomes, A plus, B, C. So basically, you're swapping parts and pieces of things. Like an example, we can actually, let's put one more on here and then I'll just give you some classic examples of these that we'll be seeing. What's the one other kind of big, broad class of chemical reactions we talk about a lot?
Would it be oxidation reduction?
Exactly. Redox reactions. Oxidation reduction. What does it mean to be reduced or to be oxidized? What's going on in these redox reactions?
Is it when electrons are lost or moved?
Yeah, so in these, this is where you're transferring electrons from one thing to another. If something is being reduced, is it getting or losing electrons?
Getting the electron.
Say it again.
It's getting the electron.
Exactly. So I mean, it's a little counterintuitive. Being reduced, it's meaning you're being reduced in charge. You're gaining negative charge. So if you're being reduced, you're accepting electrons. Oxidized, you are losing electrons. These are going to be really important. Like most of the energy generating reactions are going to be these redox reactions. We're going to be following electrons from one place to another. We're going to see electrons that are held in high energy configurations versus low energy configurations. It's useful to think of the kind of analogy of gravity. And if I have, if I have like I have a pen here. If I start lifting it higher and higher and higher, I can have this pen. I want something with more. Here's like a staple. Maybe let me turn this off for 1 second here. Right? If I have, or even better, I have this thing here. It has a certain amount of potential energy stored with respect to gravity. Right now, if I drop it onto my desk, it will come down and make a certain thing. If I start lifting it higher and higher and higher, it's getting more and more potential energy with respect to gravity. and it can do even more work as it falls, right? So this one thing, this is a Choco Cat tape dispenser, but it can have a lot of potential energy with respect to gravity, or less potential energy with respect to gravity, depending on how high up off the ground it is. So electrons are kind of similar. Depending on how they're configured in the molecules, they can be in a situation where they have a lot of potential energy. So when you have these chemical reactions, and during these redox reactions, let's say this is an electron now instead of a tape dispenser, and during this chemical reaction, it is moved from a molecule where it's held in a high energy configuration down to another molecule now where it has a lower energy configuration. And in that handoff, energy gets released that is captured to do something useful. So these redox reactions are going to be about that. We have electrons that are high energy getting transferred down to another molecule where it's held in a lower energy configuration, and that energy is going to be utilized to do stuff in your cell. So you definitely want to think about electrons. In fact, let me just give you a couple of examples. Like for instance, whoops. So NAD is something that we're going to see. It's a critical player in cellular respiration when we get into the mitochondria and all. This is what we call an electron carrier. So this is its oxidized form when it's not connected to electrons. This is the reduced form where it is connected. So this carries high energy electrons. When you see NADH, you're thinking lots of potential energy. This thing is holding on to these electrons that it can hand off to something else as it decomposes like this. And in that process, energy is released, which is then going to be used to do things in the cell. So yeah, obviously, things go back and they go either way. So we're going to, when we get to cellular respiration, NADH is going to be a major player. And it's going to be important thinking about the electrons being part of the process that are holding on to potential energy and moving it from one place to another where it can then do some more parts of the processes. So this is just an example. So this idea of high energy electrons, in this case, the electrons are being released and they have to get captured by something. What atom is the one that typically holds electrons in the lowest energy configuration? Usually the final receptor for electrons if you're handing them off from a high energy to low energy. What atom?
Isn't it oxygen?
Exactly, oxygen. Oxygen is the thing that ultimately can grab electrons because it's kind of holding down at the lowest possible, kind of like more like kind of the floor, so to speak, for doing this gravity analogy. It's why oxygen is dangerous. It can actually grab electrons from things and oxidize things, and you can damage. Oxidative damage is when electrons get ripped off of things. So, electrons. Other things to think about, just examples of what we're talking about. If I have ATP and it goes to ADP plus phosphate, and again, ADP is adenosine diphosphate, ATP adenosine triphosphate. This would be an example of kind of decomposition, right? Or catabolism. And obviously this releases energy. But almost every reaction we're going to talk about goes in both directions depending on the conditions. We're going to see lots of situations where we have to add in energy and we're going to make ATP. It'll be a synthesis. Another place where we're going to see ATP and phosphates is going to have nothing to do with energy. We're going to see, we often phosphorylate molecules. What phosphorylation is adding a phosphate group. And here we actually are phosphorylating this ADP into an ATP, but we're going to phosphorylate, proteins to turn enzymes on and off, things like that. So we could have, if I'm doing this let's not do A. Let's call it M for some molecule. Plus ATP. And again, this is just. And what we can do is do an exchange or displacement thing and take one of these P's and swap it onto the other thing. So we could end up this phosphorylated molecule here. If I can spell. And then we'll have ADP because we lost one of the phosphates off of that ATP. Right, so this is going to be, we're going to see this a lot actually, where you use ATP not as energy, but just as a source of the phosphate group to phosphorylate things, which is going to be an important part of control in the cell, like phosphorylating things, like I said, might be turning enzymes on or off or opening or closing channels or something. So this idea of phosphorylating is important. All right, so we've talked about these main kinds of reactions. Let's continue. So in any kind of reaction, let's just do some generic reaction. It's important to rethink about this idea of chemical equilibrium. Most reactions that we're going to look at can go either direction, depending on the conditions. Some reactions tend to be, in a practical sense, are irreversible, like if they're making some gas that then goes off into the environment, so it's going to be hard to get it back into the equation. But most of the time, we have equations that go one way or the other way, depending on conditions, temperatures, pressure, amount. If you have more and more of increase the concentration, it's going to push the equilibrium this way, where we're going to start making more product. Like if we start taking A away from this side, the equilibrium will shift in this direction. Right? This class is not the class where we are going to go detail of how to calculate equilibriums and things like that. But you should have a kind of basic sense of the idea that equilibriums exist and that they shift, and that if I take A away here, that it's gonna, more of this will move the reaction this way to make more of the A. If I start taking these products away, it's gonna shift, go more this direction. Does that make sense? This is gonna be at the core of how buffers work in a few moments when we talk about the pH buffers. It all has to do with, there's a chemical equilibrium and we start messing with one or the other side and the equilibrium shifts and readjusts. What affects the rate of a reaction?
The temperature.
The temperature makes a big difference. And it's important to think about what temperature actually is. What do we mean if something is hotter or colder? What is actually on a physical level? What's going on? If you touch something and it's hot or it's cold, what is different at the level of just atoms and molecules?
A faster moving?
Yeah, exactly. So it's the energy they've got, and a lot of that energy is from motion. There's like vibrational energy, rotational energy, translational energy, things moving. So the hotter the temperature, the more energy they have. And the more energy they have, the more likely A and B are going to slam into each other and have something happen and make some product. So higher the temperature, the more energy these reactants are going to have as they whack into each other, the more likely there's going to be, the magic happening and the reaction's going to run. Right? So temperature, the higher the temperature, the faster the reaction goes. What other kinds of things affect reaction rate?
Enzymes.
So enzymes are going to be super important. And let's get back, we'll get there in 1 second because we're going to look at this in more detail. And another, I'll just put it here just in the interest. Other things are like concentration. Like I was mentioning, if you have higher and higher concentrations of our reactants here, it's more likely they're going to run into each other and something's going to happen and speed up the reaction. So higher temperature will speed it up. Higher concentrations can speed it up. But as somebody was just mentioning, enzymes. Because the fact is, the temperature of your body is pretty stable. If you want to speed up reactions, if you're in doing some industrial manufacturing and you're trying to make some chemical, you actually do create these reaction chambers where you make them really hot and speed things up. But that doesn't work in the body where things have to stay at 97 point whatever degrees. So typically we use enzymes to speed up the reactions. So and enzymes are a specific example of what more general concept?
Catalysts.
Catalysts. So let's talk about catalysts.
Professor, when you say concentration, would that be something like pH?
pH is concentration of protons, but no, I just mean concentration of the reactants in the products.
Okay.
The reaction there. So catalysts. What are the defining qualities of a catalyst?
They can be organic or inorganic.
So they can be, but that's not like a defining quality. What defines a catalyst? What makes something a catalyst or not, whether it's organic or inorganic?
It speeds up the reaction.
It speeds up the reaction. Or you could say it lowers the activation energy and makes it much more likely to actually happen or run. So this is speeding up reactions in big time, not kind of speeding things up, but making reactions go that you'd have to just wait and would really not be happening in any reasonable time scale without them. So they speed up reactions. What else do they do? Or what else? What's another defining quality of catalysts? There's one other big thing about them.
It
Well,
helps.
go
Oh,
ahead.
go ahead.
You're fine. Go ahead.
It helps to break down things.
They can, or they can actually help make things as well, depending what kind of reaction they're speeding up. But that's not a defining quality of a catalyst.
But don't they speed up the reaction, but without making a chemical change?
So you're on the right track there. So they in and of themselves are not consumed or changed.
So, do they speed up the reaction without increasing energy? Is that?
I mean, they lower the activation energy for the reaction. They make it go when, if in the normal conditions, it wasn't going to run fast on its own. But the big thing is it will speed up reactions, but is not consumed in and of itself. So like kind of the classic model. Um, let's say I have some disaccharide. Let's say this is sucrose. Sucrose is a glucose and a fructose connected together by a little oxygen there. This is table sugar. This is like, just cane sugar, beet sugar, or whatever. But we want to break it into individual sugars. Um, so let's say this is sucrose. My enzyme that breaks it apart is going to be here. It has this, what we call the active site. So it has this section that fits the sucrose. So we're going to have basically my sucrose here. Whatever the thing that is actually being acted on by the enzyme, we call the substrate for the enzyme. So this is my example here, example of a substrate. This word substrate is the generic term for what is the particular thing that this particular enzyme is working with. So we have the sucrose, there's this active site, and we say the substrate binds, the enzyme, at the active site. Well, I'm trying to, there's some kind of a hum. Is everybody muted? Oh, it's gone. So what happens then is when the substrate gets into the active site, things get tweaked. There's a lot of theories on exactly how this happens. The details aren't important. In fact, the details are still things people are trying to figure out. But basically, things kind of seem, as this sucrose settles into this active site, and binding, we're going to talk more about what binding means. Binding is a reversible attraction. And we're going to talk about that in much more detail, what exactly it means. It has to do with hydrogen bonds and things. But it fits both physically in the shape as well as chemically in terms of what kind of bonds it likes to do. It fits in there. Once it fits in there, it tweaks the substrate, and my enzyme is now sitting here after the magic has happened. Except this is now floating off as two separate things. So the enzyme bound the substrate, something happened, reaction happened. In this case, it was the breakdown of sucrose into two monosaccharides, but the enzyme is still just waiting to go again. That's what we mean by not consumed. So it made the reaction happen, but it did not get consumed or changed in any fundamental way. So it's just floating around waiting for the next substrate to bind and do the reaction all again. So it's very important to realize that they work by this binding of the substrate to an active site. Because maybe I can draw this active site here. That active site has to fit the substrate perfectly, or else the enzyme will not work properly. So anything that messes with the shape of the enzyme messes with its ability to do its function. So catalysts? Catalysts in general are Speeding up reactions not consumed. Organic catalysts, I realize I should have said this a second ago. Organic catalysts we call enzymes. You can have non-organic molecules act as catalysts, but in the body we're going to have organic catalysts, and then we call them enzymes. What type of molecule is an enzyme usually?
A protein?
Yeah, these are almost always proteins. There are enzymes that are not proteins. What Tom Sheck, a guy like 10, 15 years ago, got a Nobel Prize for showing that you can have RNA catalyzing reactions and acting as an enzyme. But for our purposes in this class, all of the enzymes we're going to look at are made out of proteins. And things can mess with the shape of proteins. In fact, I know from Bio 110, you know about what is the word for messing up the shape of a protein?
Denaturing.
Denaturing. So anything that denatures an enzyme is going to affect its ability to do its job. So I'll just write this more explicitly since you should be thinking about it. Denaturing the enzyme protein kind of impairs or stops its activity. What kind of things can denature proteins, can mess up the shape of a protein?
Heat,
Say that again?
temperature,
Temperature.
pH,
So
Radiation.
Yeah, so the main temperature and pH, and actually physical mixing, and can also do it. So denaturing, lose its shape. We'll talk more about this. We're going to look at the actual chemical structure of proteins in a little bit, and it'll make more sense why heating them up or changing the pH affects their shape. But for right now, just kind of introducing this idea, things like part of why we really need to worry about homeostasis with temperature, with pH. If those are going too high or too low in your body, they are going to mess up your enzymes, which are going to affect the ability for all of the chemical reactions to run in your body. So enzymes often named with "ase" suffix. Not suffice, suffix. So if you have something "ase," it's usually an enzyme. So here, an example, a type of enzyme that we're going to see a bunch. So almost all the reactions that we're going to see in the class are going to run with enzymes. So for instance, I talked about phosphorylating things. I talked about, I called it M. Let's give it M plus ATP becomes phosphorylated M plus ADP. I basically I moved a phosphate from the ATP onto this thing. It runs with an enzyme. So when I write my reactions, I will usually put another little character, another player in here, which is the enzyme. And again, it's kind of coming in and it's going out unchanged. That's a quality of a catalyst or an enzyme. And Kinase is the name of the class of enzymes that catalyze phosphorylation of things. We're going to see creatine kinase when we get into muscle metabolism. We're going to see protein kinase A and C when we get into cell signaling. We're going to see lots of kinases. Whenever you see the word kinase, you know that you are looking at an enzyme that will catalyze a reaction that results in slapping a phosphate group on something. So whenever you see the suffix ase, you know that you're thinking about an enzyme. So let's take this idea a little deeper now. So most reactions that you're going to have, you've got some, your reactants in your products and some enzyme that is making the reaction go from one to the next. But most of the reactions in your body don't happen in one step. In fact, almost none of them do. And even the simple ones happen in a few steps. So what we're going to talk about now is the idea of a metabolic pathway. And so, and if we go, we talked about, anabolism, synthesis, making things. We talked about catabolism, breaking things down, etc. All the different kinds of chemical reactions. The sum total of all the chemical reactions in your body, that's what we call metabolism. So when we use this word metabolism, we're just talking about all of the chemical reactions going on in your body. And most of these reactions do not happen in a just straightforward reactants become products. Example, one of the reactions that we're going to spend a lot of time and that you are familiar with is cellular respiration. What does cellular respiration look like as a simple chemical equation?
It's H12O6.
So that's that's glucose. And we add in some oxygen, and it's basically the combustion of glucose, right? Glucose becomes six CO2s plus 6 waters, plus energy. This is the combustion of glucose. This is the reaction that describes cellular respiration. It looks really simple. We are going to spend an entire day of our class actually looking at the details of how the cell makes this happen. Again, if you want it to be really simple, you could light some sugar on fire in the presence of oxygen, and the energy will be released as light and heat. But that's not what we want to do. We want to have the sugar break down, and we want this energy to be captured in this usable form of ATP. And the actual process is going to be really complicated. So we're going to start, what I would say is we're going to start with sugar, and we're going to end with the ATP, but it's not going to be a simple little equation like I've drawn here. It's going to start with sugar. So let's start with glucose. I'm going to just say this is A. This is our beginning part. The first part of, so what we're describing now is this idea of a metabolic pathway. So even if this is my overall description of what ultimately happens, it actually happens in many small steps, these little steps along a pathway. So the glucose starts But the first step is going to be, oh my God, a phosphorylated glucose. Let's call this part B. And whenever you have a step from one to another, there's always going to be an enzyme. You know, the enzyme here is going to be, what kind of enzymes phosphorylate things?
Kinase.
Kinase. This is going to be what we call a hexokinase or a glucokinase. Hexo, because it's a hexose sugar, 6-carbon sugar. So here's some enzyme that is catalyzing the movement from glucose to phosphorylated glucose. That's obviously not ATP. In fact, this is going to be the first step of lots and lots of steps. This is going to go from B to C. And there's going to be some other enzyme that runs there. And this is going to go, if we just start with the first part, which is glycolysis, there's going to be 10 steps. A, B, C, D, E, F, G, H, I, J. You know, we'll end up J here, we're going to have pyruvate here. And at each step, there's going to be some other enzyme running from one to another. So and then there's going to be more steps even continuing ... until we get, let's say, to Z, which is like our ATP, which is what we want. So at each step, you are making molecules that are not your final products. So these molecules that are not your final products we call intermediates. So this phosphorylated glucose is an intermediate of cellular respiration or glycolysis specifically here, because it is made during the process, but it's not the final step. You take that and then you go to the next step and turn it into something else. And again, in each step, there's always some enzyme. I'm going to say here's enzyme B. Here's like, you know, enzyme, I'll call it enzyme I, whatever. So this is this idea of a metabolic pathway. You don't actually go just from A to Z in one step. You go A to B, B to C, C to D, D to E. You know, and how many steps depends on which particular metabolic pathway you're looking at. Does this basic idea make sense?
Yes.
All right, so let's talk about some of the benefits to this. So one thing is metabolic pathways can have points of like kind of off ramps. Like let's say you have enough ATP already. Your body doesn't need to make more ATP, but you're starting to break down sugar that you ate. What do you do with excess energy that you've just eaten that is not going to be used right now for ATP?
You store it?
Store it. And what's one of the ways to store energy?
Potential energy.
It's going to be stored as chemical potential energy. What particular molecules does your body use to store potential energy for long term?
Fats.
Yeah, exactly. So there's going to be like some off ramp. So if this is J, it'll be like K prime, J, H, I, J, K, maybe L prime, ... And we're going to end up with, fat. And again, there's going to be other enzymes that are running these steps. So depending on what my body's needs are, I can run this metabolic pathway and continue it this way. Or the first steps are the same, but then there's an off ramp where I can go off and take this fat pathway and make fat and store the energy instead. And there might be other pathways to make, actually this off-ramp has yet other off-ramps to make like cholesterol, to make parts of your cell membrane or make steroid hormones. There's lots of different possibilities. Um, and what is going to determine which path this takes? If I'm at step J, how do I know if I go down towards ATP or go down towards making fat?
The concentration for the next step.
It can be concentrations, that can be part of it, and also it can also be which enzymes are active. Again, we're going to see ways that I talked about you can phosphorylate things to turn them on and off. You can turn on and off different enzymes and make this reaction go one direction or the other direction. Or it could be about concentrations as well. So we can have off ramps. Another thing, if you're trying to get ATP, is the only way to get ATP from eating sugar?
No.
What's another way you can get ATP from your diet? What's another way you get energy from your food?
Proteins or
Carbs.
fat.
Proteins, exactly. Exactly. So proteins, fats. These are going to have their own steps, but they ultimately are going to come in and they'll merge. So I can have on-ramps where I start with some other initial reactant, some other initial stage, but ultimately the final steps are the same to make ATP. So in this metabolic pathway, here I'm kind of showing cellular respiration going from glucose to ATP, but you can have lots of flexibility where you have other things that start but then merge on, and then the final steps are going to all be the same. Or else you can have these off ramps where we have the first steps of breaking down the sugar, but then we take an off ramp and make fat instead of making ATP. So this idea of metabolic pathway is really important. Are there any questions about what I mean by a metabolic pathway? I'm realizing I should have just had this ready to go, but I'm going to do a Google search right now. I'm going to share. Just to kind of give you a sense. What? Oh, this is Met Gala. This is not metabolic pathway. Here we go. All right, this is a classic. And let me try to zoom this a little bit. Like right here, you are looking at metabolic pathways. Here is starting at actually the first steps of the glucose going to the phosphorylated. Here's phosphorylated fructose going down to pyruvate. These are all steps of a metabolic pathway. I'm kind of let me maybe get my annotator. Draw. Each of these things is an intermediate. Each of the arrows is going from one intermediate to the next intermediate. Pyruvate becomes acetyl-CoA. Then we're going to have more stuff going on in the mitochondria. Each of these circles is an intermediate. Each of the arrows is the step from one intermediate to another intermediate. And what you're looking at on this chart is just a sampling of all the metabolic pathways that are going on in your cells all the time to run all the chemical reactions. If you were in a biochemistry class, you would just spend the next 4 months learning about all these different metabolic pathways and how they work and what they are. In our class, we are only going to focus on the mainly the one that breaks down sugar and helps you make ATP and a few of the other ones. But metabolic pathways, as you can see just on this whole thing here, it's really complex. and lots of things all coming in and feeding off of each other. Well, I thought I cleared that. Hold on a sec. Clear drawings. More examples. Just to kind of give, I just want you to have a sense of how kind of complicated it is, and how the reactions don't happen in these simple ways. The reactions happen in these complicated chains, and that those chains of reactions have on-ramps and off-ramps, and every step is catalyzed by another enzyme. And we'll talk a little later about different processes in the cells that can actually control enzyme activity and make reactions go or not go. So does that make sense, the idea of metabolic pathway? Okay, metabolic pathway. Let's continue. Looking at, I was going to get through so much more here. Let's talk a bit about mixtures again. We introduced mixtures in lab. Again, typically, you have your solvent, which is whatever is in kind of the majority. In our class, the solvent is almost always going to be what?
Water.
Water, exactly. And then we have our solute, which is the thing that is dissolved in the water. Just briefly review what I mentioned in lab. We have true solutions. In fact, let me just use the little type tool so we can just do this faster. And you can have true. You'll rue the day you saw the solution. True solutions. So solute never settles. And does not scatter light. So solute never settles. It means you can walk away from this and come back next month and the solute is still dissolved in there. It hasn't come, just gone to the bottom due to gravity. Does not scatter light means it doesn't look cloudy. It looks kind of clear and transparent. This is like sugar water or salt water, things like that. We talked about colloid. So solute never settles. But does scatter light. So this is typically when the solute molecules are big. They're usually harder to get into solution. If you're making starch makes a colloid. If you are mixing starch with water, you can get it dissolved, but it's a lot harder. If you're trying to just make sugar water, you just put a spoonful of sugar and you mix it, you stir it, and you're done. If you're trying to make a starch solution, you've got to heat up the water and stir it for the next, half an hour, and eventually it'll be done. But if you just take some starch and put it in there and mix it around, it's not going to work. So, but once it's in, it doesn't settle. and it scatters light, which you saw in the lab with the cloudiness when you looked at that jar of starch solution. You could see it looks kind of milky or cloudy. And then the last thing we talked about was a suspension. And here the solute eventually settles. Okay, the idea here is the solutes are large enough that they are affected by gravity. Gravity is stronger than whatever little hydrogen bonds are pulling them up and holding them with the water. So suspensions, again, we talked about your blood with the cells is a suspension. If you just left your blood, sitting, the cells eventually fall to the bottom. Or when we do hematocrit, we're going to speed that up. We're going to take your blood and put it in a centrifuge, and it just pulls all the cells down to the bottom. It's basically increasing, the gravitational force. So suspensions are important in the body, like again, your cells in your plasma. Colloids as well are important. The cytosol in your cell is a colloid. Colloids are, we're not going to get into the detail, but they get complicated. They have what they call cell to gel soul transitions, where it can be more fluid and more kind of gelatinous and then back to fluid. So they can get complicated, but for our class, don't worry about it. So you should know, and again, I mentioned suspension also becomes important because a lot of medications are formulated as suspensions, right? So if you have some medicine that is a suspension, and then you're gonna this is a bad spoon, and it's like, here's your little patient, and you're trying to feed them this drug. What do you have to make sure you do before you feed them this suspension?
Shake it.
You got to make sure you shake it, because the stuff is probably all settled on the bottom. So it usually says shake well. So the other thing we need to talk about right now is how to specify the concentration of the solute in the solution. So we're going to spend some time looking at that. So, or I should say specifying. So specifying concentration. And concentration is always going to be a ratio between, amount of solute per amount of solution. This idea of, it's not the amount of solute, it's this ratio of, like, for instance, like think about if you're in the ocean, and think about if you dip a cup in and you have just one little cup of the ocean water. If you think about the concentration of the salt, the concentration of salt in my cup of ocean water and the entire ocean is the exact same. The amount of salt per solution. But if you think about the actual pure amount of solute, there is so much salt in the ocean as a whole compared to the amount of salt in your cup of ocean water, right? So concentration is not just the amount of solute. It's always about amount of solute per amount of solution. It's always this ratio. What are the different ways we use to specify concentration? Oh, come on.
Isn't it the amount of moles per solution?
And what do we call that? So that's one of the really common ways.
Molarity.
Yeah, so molarity. So this is going to be moles of solute per liter of solution. For this to make sense, we got to make sure people remember what a mole is. What is a mole?
Mole is the amount of something, Avogadro's number.
So you're definitely on the right track. It's the amount of something, and it's related to Avogadro's number. So we want to be a little more explicit, a little more specific. But that's, yeah.
The amount of molecules?
So now if we take Chris and Raina together, we're getting someplace here. So Avogadro's number of molecules or atoms, right? Avogadro's number is 6.02 times 10 to the 23rd. Atoms or molecules. This is a huge freaking number, right? This is 6, then 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It's this many atoms or molecules of whatever, of sugar. This many sugar molecules, this many salt molecules. People talk about the analogy of a dozen eggs. If you think about eggs, you go to the store, you don't just buy a single egg. Eggs come in this convenient amount. A carton of eggs is usually like a dozen eggs. So you buy a dozen. And that's a nice amount to keep in your fridge. This many atoms or molecules, this is about the amount of this particular stuff that makes a little pile in your hand. It's actually a practical amount. Atoms and molecules are infinitesimally, they're super, super tiny small. This many is a practical amount. 1 mole is the amount you can actually deal with. If I wanted to get 1 mole of sodium chloride, how would I actually practically measure it out? You're obviously not going to count out this. You can't do that. How can you practice?
Weigh it in grams.
So you are going to weigh it, and how do you know how many grams?
Based off the molar mass.
Yeah, again, you go to the periodic table and you add up, you realize it's like 58.5 grams per mole for sodium chloride. And so if you weighed out 58.5 grams of it, you got a mole of it. Right? So that should not feel, that should feel familiar to you. So there is a simple conversion between the real world weighing out the stuff and the amount of moles it is. It's just the atomic weight. But ultimately a mole is an amount of stuff, and how much of it? It's this many, Avogadro's number of atoms or molecules. Atoms, if we're talking about an element, like if I had a mole of carbon, it would be this many carbon atoms. If I had a mole of glucose, it would be this many glucose molecules. But it's just the number of atoms or molecules. And it's, again, converted into the real world of grams simply with the atomic mass, atomic weight. So that makes everybody, we are going to use molarity all the time. So you want to make sure you know what a mole is, that you know what molarity is. We often are going to use millimolar. Milli, what does the little m stand for? In metrics.
10 to the minus 3.
10 to the minus 3. right? So if I have 0.02 molar, this would be the same as 20 millimolar, right? To go to milli, you just move the 1, 2, 3. Move the decimal point over. So I will, we'll say 0.3 molar, or we'll say 300 millimolar interchangeably, because they're the same thing. Sometimes it's just kind of more convenient to write out like 300 rather than 0.3. So, I'll talk a little more about metric units, but you need to make sure you feel comfortable with metric prefixes. What is milli versus kilo and things like that. Continuing on. So molarity. There is another concept related to molarity. So I am assuming you know molarity. There's no way, if you pass chemistry, you have to have a pretty good sense of molarity. So the thing that you might not have seen is the idea of osmolarity. So let's look at osmolarity right now. Which is a little similar but fundamentally different. So when we think about osmosis, whether or not water wants to move one way or another way across a membrane, the water isn't caring what solute molecules are there. It just matters how many solute molecules. So osmolarity is looking at the sum total of all solute particles rather than any particular, like sodium chloride or sugar or whatever. So osmolarity is going to be the number of moles of total particles per liter of solution. So again, the fundamental difference here is moles of total particles, no matter what those particles are. We're not looking at the solute. We don't care what they are. And this is going to lead to some interesting things. Let's say I have, let's say I have 2 molar glucose and 2 molar NaCl. So these are equal in terms of their molarity. This has 2 moles of glucose per liter. This has 2 moles of sodium chloride per liter. If we start thinking about osmolarity, though, things get a little weird. The best way I know to do this is dimensional analysis. This is where if you've took like Chem 114, you've done dimensional analysis. I'm not sure they do it in like Chem 110. It's kind of more as you get more formal into chemistry. This class. If you haven't looked at it, then you'll learn it now. It's a good way to interconvert things. The basic idea of dimensional analysis is you start with what you're starting with, and you want to turn it into something else, but you do it by basically conversion factors that will ultimately convert. Like for instance, what is by definition, what does 2 molar glucose mean? We just talked about what molarity means. What does it mean if it's 2 molar glucose?
The number of moles of the solute per unit.
So more specific, like what? Go back to the actual definition. Like how many moles in unit of what?
The 0.02, so it would be 40 millimeters.
What? Millimeters are length.
I mean, yeah, but going back to the Never mind.
So go back to the definition. Go and look on your notes. What is molarity?
It's the number of moles of solute per unit.
No, unit is
Liter solution.
per what?
Liter solution.
Per liter of solution. Right. So, and if I am 2 molar glucose, what does that mean specifically? Pick the
2
number.
moles per liter.
Say it again.
2 moles per liter.
And since it's molar glucose, it's going to be 2. We want to be as specific as possible here because it's going to matter.
Moles of glucose per liter of solution.
Yes. So it matters in this kind of case that you actually are, you can't just say unit. You have to, it's liter of solution. You can't just say moles because we're going to have moles of particles or moles of glucose. That's the whole point is we're going to try to get osmolarity, which is going to change moles of what. So this is by definition what 2 molar glucose means. And if I want to get the osmolarity, I want to have moles of total particles per liter of solution. But I look here and it's moles of glucose per liter of solution. So I need to convert this. And I'm going to use a conversion factor. You basically multiply times 1. Moles of glucose I want to cancel out. So I'm going to put moles of glucose on the bottom. I'm going to want to have moles of total particles on the top. And then what is the relationship? If I put glucose into solution, 1 mole of glucose becomes how many moles of particles?
1.
1, exactly. Remember, it doesn't dissociate. So every glucose is just a particle. And then if I multiply this out, this is just 2 times 1. This is going to be 2. And again, moles of glucose cancel out. So I'm going to have 2 moles of particles per liter, which means 2 osmolar. So you might say, big deal. All right, it was 2 molar and it's 2 osmolar. But now look what happens if we do the same thing with sodium chloride. So by definition, what does 2 molar sodium chloride mean?
Is it that there's 2 moles of sodium and 2 moles of chloride?
No. If it's just the solute. The solute is sodium chloride. So it's the same by definition. 2 molar sodium chloride means, just by definition.
2 moles of particles per liter solution?
No. Go back to the definition of molarity. Here. So if I have, I don't know, if I have, 3 molar foxes, I just have 3 moles of fox per liter. Or if I have 3 moles of glucose, it's 3 moles of glucose. Or 3 moles of NaCl is 3 moles of NaCl per liter. It's just moles of solute. Whatever that molarity is that many moles of that per liter. Right? That's just the definition of molarity. So if I go back here now, if I have 2 molar NaCl, what does that mean by definition?
2 moles of
2
sodium
moles
chloride
NaCl.
Per liter of solution.
yeah.
Yes. So you're going to make sure that you're going to need to do this. You need to understand this. We're going to be using molarity constantly. We're going to be converting between molarity and osmolarity a lot. So this isn't, again, just me like saying something that you can then forget. Whew, let's move on to the stuff that's not confusing me. This has to make sense. And then I have my definition, molarity, 2 molar NaCl. Now I want to convert it to osmolarity. Again, I'm going to do a similar thing. I don't want moles of NaCl on the top. I want moles of total particles on top. So I'm going to do a conversion again. But now, what is the conversion between moles of NaCl and moles of particles? What happens to every NaCl that goes into the water?
It separates.
It separates.
That's me.
Right? Every NaCl becomes 2 independent particles, an Na and a Cl that are their own independent particles, are going to exert their own osmotic pressure on their own. So if I do the same kind of conversion factor, I'm going to have every mole of NaCl is actually going to be 2 moles of particles. Does that make sense?
Yes.
Then if we cancel moles of NaCl and we multiply through, it's like, oh my God, we've got 4 osmolar, right? 4 moles of particles per liter. So the osmolarity is twice the molarity in this case. So this is going to be critical. This is going to be absolutely critical to understand when the molarity is equal, when the molarity is different from the osmolarity.
Why is it 2 moles particles?
It's all that stuff we did in class on Thursday. Remember NaCl goes into aqueous solution? What happens to the NaCl? And you put it in the water. It was on the quiz, on the warm-up quiz as well today.
It dissociates.
It dissociates. Right? The Na plus becomes its own independent thing. The Cl minus becomes its own independent thing. And they're each doing their own little deal with making hydrogen bonds with the water. So each Na plus is its own deal. Each Cl minus is its own independent deal. That's why it conducted electricity. We had the freely moving charges. So it all kind of ties in. So does that make sense?
Yeah, I understand now.
Yeah, so what if I had 2 molar calcium chloride? And I put that, what would be the osmolarity of that? Right, by definition,
6.
what is 2 molar calcium chloride mean?
2 moles of calcium chloride per liter solution.
Exactly. And then the conversion now is instead of moles of calcium chloride on the top, we want moles of particles. So one of the nice things about dimensional analysis, you're trying to forget or trying to remember what goes on the top or the bottom. We want to cancel moles of calcium chloride. I'm going to put moles of calcium chloride here. How many particles? I want moles of particles on the top. How many moles of particles am I going to get? 3. Every calcium chloride becomes a calcium and 2 chlorines. So this is going to end up being 6 osmolar, right? So, and again, osmosis, we're going to have two labs that are just pushing the idea of osmosis. Osmosis is so critical and key to so much going on in our class. And osmosis is driven by the concentration of total particles, which we measure in osmolarity. So you really need to understand osmolarity. It's going to be an ongoing theme in our class. So any initial questions about osmolarity or clarifications?
Yeah, I'm a little confused on the glucose part. Does glucose not dissociate in water? Is that why the osmolarity was the same as its regular molarity?
Exactly. Right? It dissolves because there's charge imbalance, but overall it stays as an intact glucose molecule. It doesn't break apart in any way. So one glucose molecule is just one particle floating around in the solution. Whereas the ionically bonded, so things that are covalently bonded, you're going to basically have molarity and osmolarity are going to be the same. But things that are ionically bonded, that dissociate, you're going to have osmolarity going to be larger depending on how many particles it dissociates into. So that makes sense?
I also have a question. Is osmolarity always dealing with water as the solution?
Yeah, because think about, we'll talk about this in more detail, but again, osmosis is at the core of so much. What the heck is osmosis? What is the definition of osmosis? This is, I know you talked a lot about this in Bio 110.
Isn't it like the movement of water over a membrane?
Yeah, so this is just the diffusion of water across a semi-permeable membrane. Right, so osmolarity doesn't make any sense if we're not talking about a water and aqueous environment, because the whole idea of osmosis is the movement of water. So, I'm sure you could adapt it to different situations, but all of our examples of where we care about osmolarity are going to be in aqueous solutions, because we're worried about how does this affect the movement of water across the cell membrane. And we'll talk a lot more about osmosis. And again, we're going to be doing lots of labs about osmosis. It's 9:45. For just completeness, I will throw in one last way that we often specify concentration, and then let's take our break. So another way, so again, specifying concentration. There's molarity, kind of the classic moles per liter, moles of solute per liter solution. There's osmolarity, which is moles of particles per liter of solution. And then we also, and the problem with both of these is that this is more for a science lab, because if you want to actually weigh out a mole of sugar or a mole of salt, you have to go to the periodic table and calculate, well, how many grams is that and whatever. So in a practical world, you often just use percent solution. And this is going to be another important way to specify concentration. So this is usually, this can be by weight or by volume. But basically, like, grams of solute over grams of solution. right? So this is not dealing with moles and stuff. It's just stuff you can weigh. And in fact, it's easy to make a percent solution pretty easy. So water, how much does water weigh? If I have 1 mil of H2O, how much does that weigh? Or what's the mass, I should say?
Is it 100 grams?
No. So we should so 1 mil, which is right 1/1000th of a liter. This is kind of a typical, this is all metric volume. The relationship between mils and length, if I take a cube, that's a centimeter on each side. So this is 1 cubic centimeter, or 1 cc. The volume of 1 cubic centimeter is the same as 1 mil. Right? So like, in fact, when you're like drawing up some medication to shoot somebody up, you could do it in cc's or in mils. It's the same thing. Cc's and mils are synonymous. And 1 cc or 1 mil has a mass of 1 gram. So, the metric system is so much easier than the imperial system because things just make sense and interconvert really easy, right? So, let's go back to where I was here. And I made a mistake here. Percent solution is going to be times 100. So it's going to be grams of solute over grams of solution times 100. So if I wanted to make a 4% sugar solution, it gets really easy. If I wanted a 4% like sugar, all I'd have to do, I could say, let's take 100 mils on the bottom, and 100 mils is basically 100 grams. And then weigh out 4 grams of sugar, and I'm done. So if I basically put 4 grams of sugar in 100 mils of water, I basically have close enough 4% sugar solution. So that's one of the reasons this is really nice to use in a practical way too. It's just really, you don't have to do any weird calculations. It's really easy to mix up a solution that's specified as percent. Things that are liquid and you have to dilute, then it could be percent by volume. Like what percent of the overall volume is the stuff that we put in there. We'll look at this again. We'll revisit this after our break because I do want to. I'll show you something interesting. But let's take a break.